The objective of Lab 3 was to find the mass of a black hole by using information from a star orbiting it. The mass could then be calculated by using the star's net force and momentum vectors. The mass I found was 4.975 times 10 to the 31st kilograms. In order to calculate the mass of the black hole, the principles used are the momentum principle and the law of gravitation. The momentum principle can be defined as the change momentum equals the change momentum in its perpendicular direction plus the change momentum in the parallel direction. The change momentum can also be written as m delta v over delta t, which is also ma. Therefore, dp over dt is equal to F net because F net is ma. Newton's law of gravitation is defined as g_mm over r squared. The only force in this system is the gravitational force from the black hole, so we can treat F net equal to the Newton's law of gravitation. The initial conditions included the star mass at 4.3303 times 10 to the 27th kilograms, delta t, which is equal to 86,400 seconds, or 1 day, and the initial position of the black hole, which is -1 times 10 to the 10th in the x direction, and 5 times 10 to the 10th in the y direction. We can now move into the Python code and set our initial conditions. The mass of the star can be set here just using the value given, and the black hole can be set using its initial position. I also gave it a shape and radius so that it shows up in the simulation. Then delta t, we can use our 86,400 seconds and use that as our time interval between the data points. In the first calculation loop, we can enter our equations for momentum and force. Starting out, we have to set our initial momentum and our final momentum. This is just given by the star's mass times its initial velocity and its final velocity, because p equals mv. Delta v is just the final velocity minus the initial velocity, and delta p is just the final momentum minus the initial momentum. Now in this section, it is essentially these equations written out in code form. First, dp over dt is the same as delta p over delta t. And using Newton's second law, we know that F net is equal to dp dt. Here we set our values to find dp dt in the parallel direction. And that is just given by dp dt, or the magnitude of dp dt, times p hat. And then now we can calculate Newton's second law in the parallel direction to then be dp dt in the parallel direction, since we know the two are equal. In the perpendicular direction, we know that it's dp dt minus dp dt parallel because of this equation right here. And then finally, for Newton's second law in the perpendicular direction, we know that F net perpendicular is equal to dp dt perpendicular. Here's where we can use Python to calculate the mass of the black hole. First, we have to find the distance between the star and the black hole, because this is the value r that we then use in our F net equation. And this is just given by the star's position minus the black hole's position squared at each data point. Now to find the mass of the black hole, we know that F net is equal to the gravitational constant times the mass of the black hole times the mass of the star over r squared. So we can set our gravitational constant here and then rearrange the equation so that the mass of the black hole is equal to the F net times r squared over the gravitational constant times the mass of the star. And then written out in code form, it looks like this. Finally, we can then edit the aeroscale so that the vectors are visible in our simulation. Here I found that the value that worked best was 0.13 times 10 to the negative 13th. And then at the end, we can tell Python to print out our values for the magnitude of the net force, the magnitude of the net force in the parallel direction, and the magnitude of the net force in the perpendicular direction, as well as the mass of the black hole. We can now run the simulation and see the path of the star as it travels around the black hole. The arrows that appear are those of the net force vectors. The yellow is the net force, and the blue is the net force in the perpendicular direction, and the black is the net force in the parallel direction. You can see that as it travels around the black hole, the values increase because the gravitational force is stronger when it gets closer, and weaker as it gets farther away. Python is then able to print out our force values as well as the mass, which are given here at the top. One component of this lab is looking at force and momentum and trying to determine the difference between the two. When you look at net force and change in momentum, they may be equal, but there is a fundamental difference. Net force is what causes a change in momentum. So when you're looking at an object speeding up or slowing down, that is a force that then changes the momentum. Or if an object is curving, that is because of a force that changes the momentum in the perpendicular direction. So these changes in momentum can only come about from changes in force. A new black hole with a new mass would change the net force acting on the star. This new net force would in turn cause the star to orbit in a new motion with different perpendicular and parallel momentums that reflect this new gravitational force. Since the star is still moving at the same speed and has the same position values, the mass would have to be the same. The mass changing impacts the gravitational force, which in turn impacts the position of the star, making it impossible to have a black hole with a different mass, but have a star that keeps the same orbit.